Hi everybody, this video goes over section 3 of chapter 8, and here we are going to talk about the concept of vectors from a geometrical perspective. We will start off by introducing some nomenclature to you guys. Then we will talk about how to compute the sum of two vectors. We will use that to solve some incline applications and also to solve some navigation applications. Now, the quantities that we have been using thus far in this course, and probably thus far in your mathematical career, have been scalars. There are basically quantities that involve only magnitudes, so basically one number or one item is all you need to describe those particular quantities. Primary example, speed of the car. Another example, of course, is the current temperature, 60 degrees. In some ways, also a third example might be your weight. How much do you weigh? I weigh about 200 pounds. That's my weight. Those are all scalars. One number is all I need to describe those things. A vector, at least from a geometrical perspective, is a quantity that involves both a magnitude and a direction. So two items are required to specify a vector. Examples of a vector is velocity, which is different than speed because speed is essentially the magnitude of the velocity. But once you include a direction, such as north, or 0 degrees relative to true north, you now have a vector. And it turns out that 90 miles per hour true north is different than 90 miles per hour true west, and actually is the opposite of 90 miles an hour in the direction of south. And another example of a vector, of course, is right here, 45 miles an hour in the westerly direction. But notice we have two items that specify velocity. The magnitude, which of course is the speed, and then the direction. Force is another example that actually is a vector. As a matter of fact, if you weigh 200 pounds like I do, then I'm applying a force straight down of 200 pounds. So I'm basically applying a force of 200 pounds directed towards the center of the earth. Now, if you are lifting a 120-pound object at a constant velocity, then you are applying a force of 120 pounds in the upward direction. And if you're pushing 120 pounds to the right, then you are applying a force whose magnitude is 120 pounds and the direction of that force is to the right. So once again, for vectors, you need two items to specify this specific quantity. How are vectors described, at least graphically? Well, basically as an arrow. Or as the book says, a line segment with an arrowhead at one end, which, well, you know, it's an arrow. The length of the arrow indicates its magnitude, and then the direction of the arrow indicates its direction. That's kind of redundant, but that's pretty much the case. However, when we do define directions, we usually have to do it relative to some frame of reference. So here, if you could almost interpret this as the x-axis, this is our frame of reference for actually for quantifying the direction of these two vectors. Okay, now how do we name a vector? Well, essentially there are, well, possibly three ways. The first way is to use two capital letters. The first capital letter indicates where the beginning of the vector or its originating point, and the second capital letter indicates its terminating point. Okay, so here is the vector AB. It starts at A and it goes to B. Here is the vector BA. It starts at B and it goes to A. And as you can see, they have the exact same magnitude, but the direction is completely different. Now, when we specify the vectors, we can usually, sometimes we will embolden the AB if we can, or other times we will just put an arrow on top of AB to indicate that is indeed a vector. Once again, notice that AB and BA are not the same vectors. They may have the same magnitude, but they have completely different directions. As a matter of fact, BA is the opposite of AB. And if you added these two together, you would get the zero vector, which is a vector that has zero length. The other way to identify vectors or to name a vector is essentially using either a lowercase or an uppercase letter right in the middle of the vector. Now, two vectors are considered to be equal if and only if they have the same magnitude and direction. The only two numbers that matter, remember, vectors are specified by two numbers, magnitude and direction. So if they are both the same, then the vectors are said to be equal. Furthermore, if you add two vectors together, you get, you guessed, you guessed it, a vector. And a vector addition is commutative, so a plus b is equal to b plus a, just like in the real number system. However, the sum of the vectors a and b is called the resultant of a and b. Now, there's a few other vector properties to talk about, and these are consistent with the real numbers. Once again, for every vector a, there is a vector negative a, and we call that the opposite of a. Basically, it has the same magnitude, but the direction is opposite of a. And if you added those two together, you would actually have a vector with magnitude 0, and we would call that the zero vector. It's also considered the identity vector for the entire vector space. Okay, now we want to talk about at least the graphical way, the graphic way of adding two vectors. And there are basically two approaches. One is called the triangle approach. The other one is called the parallelogram approach. We're going to talk about the parallelogram approach because this is the one that's most consistent with our definition for the law of cosines. So this is how this works. If you want to add a and b together, you place their initial points so they coincide, just like this. And notice that we actually have 1/2 of a parallelogram. So we can complete the parallelogram using b for this side and a for that side. And then the resultant, or the sum of a and b, is going to be the vector defined by the diagonal, which starts at the same initial point as a and b, and then terminates on the other side of the diagonal. So this right here is a plus b. And notice that since this length right here is b, if we know this angle, then we can actually compute this magnitude using the law of cosines. So let's go over some of the properties of a parallelogram. First thing is, a parallelogram is a quadrilateral whose sides are parallel, hence the word parallelogram. Also, the opposite sides are equal. As a consequence, as you can sort of see here, the adjacent sides are supplementary. So if we know this angle right here between A and B, then we can figure out this angle right here. And then once we figure that out, we can use the law of cosines. Two other properties which really probably will not serve us all that well is the diagonals happen to bisect each other. However, the diagonals do not bisect the angles of a parallelogram. That only occurs when the parallelogram is a square. Okay, and then the last thing we want to mention in terms of nomenclature is this thing called the equilibriant. Well, if the vector v is the resultant, then the vector minus v is the equilibrant. If I said that correctly, equilibrant. So how do you find the resultant? Well, you take a and b and you get this vector v. And then how do you find the equilibrant? Well, it's going to be the vector with the exact same magnitude, but opposite direction. And that brings us to our first example. Here we want to find the magnitude of the equilibrant of the forces of 54 newtons and 42 newtons acting on a point A. If the angle between those two forces is 98 degrees. Then we want to find the angle between the equilibrant and the 42 Newton force. Okay, so here is a diagram of those two forces. This right here is point A. And before we can figure out what the equilibrant is, we probably need to find their resultant. And remember, the resultant is basically the vector A plus B. Okay? So to find the sum, let's go ahead and construct our parallelogram as best as I can. Okay, so if this is 54 newtons, this is 54 newtons. If this is 42 newtons, then we have 42 newtons over here. Okay, and then the vector is going to, the resultant is going to start here and is going to go to the other side of the diagonal, and that would be the resultant. Apologies for the not so straight lines. Okay, so and notice here that we have a triangle. We can go ahead and label this triangle. Let's call this point A. Let's call this point B. And let's call this point C. And that's the case. We have the triangle ABC. Now, if this angle is 98 degrees, then this angle is going to be its supplement, which is 180 minus 98 degrees, which would give us 82 degrees. And now we have everything we need to actually compute the magnitude of the resultant and also the magnitude of the equilibrant. But also notice that since we actually label these things, we can actually call the resultant the vector AC, which is equal to the vector AB plus BC. So if that's the resultant, then the equilibrant maybe it's called, is going to be the vector CA, because remember the equilibrant is the opposite of the resultant. Okay, maybe we can put little lines over here to remind us that these are vectors. Okay, so now we can go ahead and compute the magnitude of this. So we are going to have that the magnitude of AC, which once again is also the magnitude of CA, is going to be equal to, well, 42 squared plus 54 squared minus 2 times 42 times 54 times the cosine of 82. And that will give us a value of 4,048.71 and a few other digits. If that's the case, oh, no, I'm sorry, this is going to be the square of the magnitude. AC squared is equal to all this. And that means that AC, the actual magnitude, is going to be equal to the square root of that, which will be 63.63, and we can round that up to 64. But for the rest of our computations, we're probably going to want to use this. Okay, now to find the angle of the equilibrium relative to 42, we first need to find the angle of the resultant relative to 42, and once we have, because that's easy, because we can find that using the law of sines, and then the angle of the equilibrium relative to 42 will be the supplement of that. So we can find the angle using the law of sines, because essentially we're looking for the sine of A in this triangle right here, and we know this angle, and we know the length of all three sides now. This is 63.63. And so law of sine seems to be like the appropriate way to go. So we will have that the sine of A is equal to the sine of B divided by the opposite side, which is going to be 63.63 times the side opposite to A, which is 54. And when you do that math, you will have that the sine of A is equal to 0.840397. And if that's the case, then A is equal to 57.18 degrees. And that right there is the angle of the resultant. So this is the angle of the resultant, or AC. So the angle of the equilibrium will be 180 minus that. So the angle of the equilibrium, this angle, is going to be 180 minus 57.18 degrees. And that will give us 122.82 degrees. So then the angle of the equilibrium will be, or this angle of the equilibrium will be 122.82 degrees. Now, in your homework problems, you'll be able to round to the nearest newton and the nearest angle. So the magnitude the magnitude of the equilibrium will be 64 newtons, and then your angle will be 123 degrees. Okay, the next class of problems that you will encounter are what we call incline problems, and they are actually applications of physics where we want to account for all the forces acting on the object and apply the force that we need to apply to keep an object in equilibrium, or so that all the forces add to zero. And here is our first example, at least in this particular area, and we want to find the force required to keep a 2,500-pound car parked on a hill that makes a 12-degree angle to the horizontal. So notice that we have one force, and that one force is going to be the weight of the car, and that is going to be a 250-pound force going straight down. Now, this can be the sum of two forces, where one force is perpendicular to the plane, or to the incline, and then the other force which is parallel to the incline. Now, the force perpendicular to the incline will be offset by what we call a normal force, which is going to be equal and opposite in the perpendicular direction. However, there is no force opposing the component that is parallel to the plane, so that we need to apply a force that is equal and opposite to this particular force. So let's go ahead and name some points here. Let's call this point B. Let's call this point A. Let's call this point C. Okay, and if that's the case, then the vector BA is the force due to gravity. And BA is the sum of BC, that's the force perpendicular to the ramp, plus the force CA, which is the force parallel to the ramp. Now, the force perpendicular to the ramp, once again, will be opposed by the ramp itself, because the ramp is basically pushing back in that particular direction. Now, the force CA, the vector CA is the force going down the ramp, and that is the amount that we need to oppose. That is the amount that we need to oppose. So the opposing vector, pushing up in this way, has to have the magnitude CA. Okay? And how can we figure that out? Well, first thing we need to do is we need to figure out what this angle is. And as you can see, I already showed you what it is, but let me walk through it. This angle right here is 12 degrees. This is a right triangle. So then this angle right here must be the complement of 12 degrees, which is 78 degrees. Well, this angle right here is a right triangle. Therefore, this angle must be the complement of 78 degrees, which, by the way, is 12 degrees. So this is a 12-degree angle. Now, also notice that we have a right triangle here. All right, this is the hypotenuse. This is and then these are the two legs. And this leg right here, this vector AC, is the leg opposite our 12-degree angle. So the sine of 12 degrees is going to be equal to the opposite, which is the magnitude of the vector CA, divided by the hypotenuse, which is the magnitude of the vector BA. Well, CA, we don't know what CA is yet. That's what we actually need to find. We know what BA is, that's 2,500. So now we can solve for CA, and that would give us that the magnitude of that particular vector is going to be equal to 2,500 times the sine of 12 degrees. And that will give us 519.7 pounds, and we could round that to 520 pounds. And that would be our answer for this particular problem. Now, this is basically a similar problem. Here we actually have a crate. It's 74 pounds. It is on a ramp, and we're assuming that all this is frictionless. And we have a force of 18 pounds pushing against the crate. And the question here is, well, what angle does this ramp have to have so that this doesn't move? Well, basically, this has to be of a high enough angle so that this particular force is equal to 18 pounds. Because if this force is less than 18 pounds, then the box will be pushed up. If this force is greater than 18 pounds, then the box will be pushed down. So we want to find that value theta that makes this side 18 pounds. Now let's go ahead and name some points. We can call this point over here A, B, and C, just like we did in the last problem. And if that's the case, then we want to make sure that the magnitude of CA is equal to 18 pounds. That's what we want. Okay, we want to find that value theta that makes that happen. Well, just like before, if this angle is theta, this angle is theta. And then we have that the sine of theta is going to be equal to the opposite, which we need to have to set at, which needs to be 18 pounds, divided by the hypotenuse, which is 74. And if that's the case, then theta needs to be the inverse sine of 18 over 74. And that would be 14.07 degrees, which for this particular problem, you would want to round to 14.1 degrees. Okay, the next two problems that we're going to deal with are navigation problems. And here is our first navigation problem. Here we have a ship is leaving port on a bearing of 25 degrees. And when we're talking about a bearing, that bearing is usually relative to either true north or magnetic north, depending upon the type of navigation situation you have going on. So this is our bearing of 25 degrees right here. Okay? Now, it travels at this bearing for 61.4 meters, so this is the vector that represents that length. Then it turns east and then travels for 84.6 kilometers in this particular direction. Okay, and the question is, how far is the ship from the port, and what is the bearing from the port? Well, if it went 61.4 kilometers at a bearing of 25, and actually this is the scale, and then turned and went 86.4 kilometers, it's going to be here. And then this will be the resultant position vector for the ship. So to figure this out, we would need to know what this magnitude is, and to find out what this magnitude is, we actually need to figure out what this angle is. And we can actually do that. Now, this is a right triangle, north, east, and our hypotenuse. So if this is 25 degrees, then this has to be the complement of 25 degrees, which would be 65 degrees. Okay, well, if this is 65 degrees, then this has to be the supplement of 65 degrees, which will be 115 degrees. And there we go. We have the length here, we have the length or magnitude here, we have the length or magnitude here, and the angle between them, and we can figure out the magnitude of this particular vector. The magnitude of the vector PE is going to be equal to this vector, the magnitude of this vector, 61.4, squared, plus 84.6, this vector squared, minus 2 times 61.4 times 84.6 times the cosine of 115, and that will, this is the magnitude squared, I apologize, I did that again, and that will be equal to 15,317.65041 kilometers squared. And if that's the case, then the magnitude is going to be the square root of that, and that will give us 123. This will be supposed to be a 3.76 kilometers, and we can round that to 124 kilometers. Okay, now we need to figure out what the bearing is. Now this is the bearing. It is going to be the sum of 25 degrees plus whatever this angle is, and we're going to call that P. But we can find that particular angle right here using the law of sines. And we will have that the sine of P is equal to, well, the sine of A, since we already know what that is, that's 115. The sine of A divided by the length of the opposite side, which now we know, but we're going to use this term right here, 123.76 times the length opposite P, which is 84.6. And that will give us a value for the sine of P of 618,336. And if that's the case, then P is going to be equal to 38.28. Therefore, the bearing will be the distance from true north to this particular vector. That's going to be 25 degrees plus 38.28 degrees, and that will give us 63.28 degrees. And for this particular problem, we could round that to 63.3 degrees. Okay, for my last problem, we have this. Here we have a small plane that's following a bearing of 70 degrees. Okay, so here's our bearing. Once again, this is true north, and of course this is basically the exact same axis, just transposed. So, but once again, we have a small plane that's following a bearing of 70 degrees at 230 miles per hour. So this vector right here, we can call that AB, represents airspeed of the plane. All right, it encounters a wind that is blowing at 25 miles per hour from a direction of 290 degrees. Now this is 290 degrees, and the wind is blowing from 290 from that direction, which means it's going this way. That's actually how they characterize wind in the weather. And that implies that we have a vector of length 25 in this particular direction. So even though this is 290, the direction in which the wind is going is actually 110 degrees, 290 minus 180. Okay? And we want to find the resultant bearing and ground speed of the plane. Well, the ground speed is going to be equal to the airspeed plus the wind, so the vector AC is the ground speed. So AB is the airspeed, BC is the wind, and then AC, what we're looking for, is the ground speed. Okay, well, notice that we have this term, and so the first thing we want to figure out is what is the magnitude of AC. Well, notice that we actually have this length, we just need to figure out this angle here, okay? That's going to be our trick, is to figure out this angle. Well, we know that this angle is 70 degrees. This line is parallel to this line, and as a consequence, we have basically an interior alternating angle. And if you remember way back when you took geometry, if this is 70 degrees, then this is the exact same angle. So from here to here is 70 degrees. Now, if this angle is 110 degrees, then this angle is 20. Okay? And if this angle is 20, then this angle, which is going to be the complement, has to be 70. So this is also 70 degrees, which means the entire combined angle is 140 degrees. So B, the angle B, is actually 140 degrees. Now we can figure out what AC is. The square of AC, or the magnitude of it, the square of the magnitude of AC is going to be equal to 230 squared. 230 squared plus 25 squared minus 2 times 230 times 25 times the cosine of 140 degrees. And that will give you a value of 62,334.5111 miles per hour squared. If you take the square root of that, you will have the magnitude of the vector. That's what we're looking for, and that will give us 249.66 miles per hour. And for our answer, we will probably want to round that to 250. For our intermediate calculations, we probably want to use the 249.66. Because we have one other thing we need to figure out. We need to figure out the bearing between the bearing of the ground speed, which is the angle from north to the vector of the ground speed. And that's going to be 70 plus whatever angle this is. Well, that is A, and we can find that using the law of sines. So the sine of A is going to be equal to the sine of B divided by the length of B, which is basically is AC, or the opposite length, times the length opposite A, which is 25. So we're going to have the sine of 140 divided by 249.66 times 25, and that will give us that the sine of A is equal to 0.0643640. And if that's the case, then A is equal to 3.6903 degrees. Okay, so that's what this is right here. This is A. And then the bearing is going to, be equal to 70 plus 3.6903 degrees, which of course will be 73.6903 degrees, but we want to round this to the nearest degree, which of course will round to 74 degrees. And that is it. And that's how we handle these particular problems. So this completes this video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.